Okay, so let's talk torsion for a little bit. We're going to be primarily starting off by reviewing some stuff from last year, kind of basically give you the basics of how to solve an indeterminate problem when involving some sort of twisting action. But essentially we're going to kind of be exploring those a bit more, doing a bit more complicated ones. Also, we're going to be examining kind of what happens when we have a tube, specifically a thin-walled tube that isn't in a circular cross-section. So we'll look at those, and we'll end up figuring out kind of what sort of stresses arise as that. In particular, we'll introduce the concept of shear flow. So if we are twisting on a bar, we're applying some sort of twisting action to a bar or a shaft or what have you, you're going to have some sort of shear stress that arises in order to counteract that twist. That's the only net force that would arise. So, it's kind of going to be acting about a certain point. You're generating a moment, basically, acting about the centroid in this case. That's the way things work. Now again, one thing you need to emphasize here, the stresses arise due to the shear strain. They're linearly proportional to one another, and there's going to be no strain at the centroid. It's the point that is twisting about. It's not there's zero net twist kind of going on there, so no strain there, and then it increases as you get out. So basically, the further you get out, kind of the more the part has to move. So you'll notice for like the same amount of twist at the center, the strain. It's the same angle of twist. The actual amount that my fingers need to move, kind of at the point of rotation, is zero at the center, where it's a lot more at the ends. They need to shift a lot more at the ends, so that causes more shear strain. Same idea here. So we've got, we know that the strain increases linearly as we get further from there. So the strain at any particular point is going to be equal to the maximum strain times the ratio of the distance from the center divided by the maximum distance to the center. So, or like the point on the radius that we're at to the actual radius of the shaft we're looking at. Now, for this derivation, we're kind of assuming that we're talking a solid circular structure. Because then we can kind of assume that everything's evenly distributed. So if we want to calculate the torque that would arise, well, each little tiny area element there is going to have its own little individual bit of torque. So the magnitude of the force on each little individual element is going to be equal to just the area of that element times the stress, and then the moment arm is just going to be that times the distance there. So we got the torque for each little moment, each little bit, and then obviously we would just integrate to get our torque. So integrating that and solving for our stress gives us this. The J here, that's our polar moment area. You'll recall from the discussion on kind of the properties of cross sections and centroids and so on and so forth section there. So what we're able to do, I didn't mean to do that. So we got our stress in terms of torque here. So that is for a circular section, a solid shaft. Again, starting at 0, varying, increasing as we get further out. If we have a tube, on the other hand, it's not. It's the principles are exactly, the base principles we're using to drive this are the same. Shear is going to be increasing linearly from the centroid, and everything needs to add up enough to counteract the torque. So basically, ends up being the same thing, except the J that we would have calculated previously needs to be pi over 2 times bracket the outer radius to the fourth minus the inner radius to the fourth, close bracket. So, and here this formula, I just took it's just me taking this one here and plugging in the J values for those two configurations. Okay, so if we know the stress that's arising due to our torque, we also know the strain that's arising due to our torque, the shear strain, because, well, we got that, because they're proportional one another, related to our shear modulus there. So, if we know our what am I trying to say here? We know our shear strain here at the ends. So let's say that angle there. If we know that angle there, then we can figure out from that how much offset would we have per unit thickness. And then we can also figure out kind of, instead of looking at it from that end, we look at it from the face. Kind of solve for our phi here. We're going to call that phi. Based upon that. So then our delta phi is going to be equal to the shear strain max dx. Or solved another way, our delta phi per over our delta phi over delta x is going to be equal to our shear strain, which is going to be equal to our TC over JG. So that's kind of the amount of twisting that this thing has per unit length locally. So if we need to find out kind of how much this thing twists over an entire length, well, if these things are functions, if these things vary, then obviously we're going to need to integrate that. So we can take this and integrate that as these things vary. So generally speaking, most of the time you're not going to have the G changing. Your material properties tend not to be a function of, they tend not to vary with distance, except, in terms of like discrete chunks. You might have a section of the shaft that's made out of one material. You might have a section of another section that's made out of a different material. So that could happen. Your torque could have some sort of distribution to it. So you could have like a torque that's being applied, you could have some sort of torque distribution, similar to how you'd have a distributed load on a beam. or like a vertical load on a beam. You can have a distributed twist. That doesn't come up as often though. The one that will typically come up will be your J of X. And that'll happen basically when your radius varies over the distance. So like we see here, where it's thinner on this end, fatter on that end. So something like that. That having been said, most of the time, what you'll end up doing is you'll end up being looking at independent sections that are, they have a constant G, a constant J, and a constant torque over that entire length. So if so, then the amount of twist over that length is just going to be TL over JG. So this is what will be used for your compatibility conditions for basically any of your torque indeterminate problems. Sorry, the bulk of them. And then, of course, some of them you might need to use this. So those are for circular shafts, circular solid shafts operating in the elastic region. Obviously, there are some situations where those conditions are not going to be necessarily adhered to, but oh well. You can adjust accordingly, but some of the assumptions made in that may be thrown out. For example, there are sometimes some plastic shafts that are designed to be operating where the bulk of the shaft is actually undergoing plastic deformation. So that there may the formulas that we've been using won't necessarily apply. Sorry, some of the assumptions that we used wouldn't necessarily apply there. So as a result, you're going to end up ending up with it. Yeah, so you're going to end. So when you kind of work through the derivation of the equation, making different assumptions, then you are going to have to, obviously going to end up with a different result. But anyways, the other thing that we're going to be talking about for torque is thin-walled tubes with non-circular cross sections. So we're specifically talking thin-walled tubes here, because basically what can happen here is if we kind of take a section of the tube here, kind of slice it up and look at it, you're going to have here, I'm going to draw this a bit bigger. That's tau alpha, tau beta. So those are kind of or tau A, tau B, I guess. So yeah, basically kind of the shear stress at this section and the shear stress at this section. And obviously, we know the way shear stress works is that it's going to be kind of acting, when it's at a corner, kind of like anytime you have shear, needs to be count. Oh, what's going on here? My tablet is being annoying. Needs to be counteracted like this. So that's why we have these forces in this direction as well. And essentially, if we look at this element, and if we want this element here to be in equilibrium, then essentially the total force that's acting in this direction needs to be the same as the total force that's acting in that direction. We're assuming here that kind of the slice we took here is kind of a constant width, but the thickness here could change. But when we basically shear stress here is kind of the same here, and the shear stress here is the same as here. So for that to be the case, then basically the stress times the thickness here needs to be the same as the stress times the thickness here. And that basically goes all the way around. So we have this concept we call kind of the shear flow, which is denote that Q. So that's just the stress, kind of the average stress in the section times the thickness. So essentially, you've got a certain amount of flow that you need. So if the pipe gets thinner, then the stress level goes up, and vice versa. And one other thing that kind of arises out of this is that you're always, essentially, like when we look at this element here, we kind of, at this top surface and at this bottom surface here, that, those are free. So there can't be any stress operating. There's no forces in this direction. There's no forces in that direction, which also means that there, at the corner here, there can't be any stresses right there, right? Can't be any stresses kind of close to this line, and there can't be any stresses close to that line. And essentially, if you're thin enough, then what you can say is that there's no room for any stresses to arise. So kind of when we take this slice here, when we're looking at the forces that are acting on this face, the only direction it can act is along this way. This way or that way, obviously. Either way, but it needs to be acting parallel to the line kind of going around here. So knowing how the shear flow works, we can to basically create an average shear going around, we need to figure out how much would that be. So looking at, if we take a section on the kind of circumference of there, look at a tiny little bit here. ds is going to kind of be the thickness of that, and obviously, sorry, I guess the width component, because the thickness is the through thickness. That's that t. ds times t is the area of the tiny little bit we're looking at, and that times the stress is going to be the force component. So that force is going to be acting in a direction that is tangential to the vector, tangential to the shape of the tube, and that little bit is going to contribute a moment. So the amount of that torque moment is going to be equal to that force vector times the moment arm, so h. So here h is just, the offset. Now again, the perpendicular offset to the centroid, based upon the directionality of the force there. So it's not just the line from the point to there, because again well, here, like say for example, say we had a shape that was like this. So if we're looking at, say, I guess this point right here, the h that we'd be looking at would be kind of the offset based upon the tangent there. So this would be our h. It wouldn't just be the distance from here to here, because there's a bit of an angle difference there. So anyways, So that's the tiny little bit, and then we just need to figure out what the total torque is by taking that and kind of integrating around the perimeter. So again, we know that this tau average t term here, that's a constant. That's that q. I'm just going to cross that out and put q there. So then we we just need to integrate this. So what we can do there is basically we can relate that to the so let me think here. So essentially, kind of if we were looking at this here, we'd have kind of that h vector, and then we would have this ds here. So that's that tiny little rectangle there. So basically, if we want to if we want this ds times this h, then basically ds times h would be twice the size of that little that blue triangle there. So if we want to figure out what the integral of the HDS is over the entire thing, then we can just take twice the area, kind of from the center of the perimeter around to all the way around. So that's where we get this relationship here between our torque and the stress. It's going to be the torque is equal to twice the average stress times T times this AM here. Or solving for our stress or solving for a Q like this. So, and that's in terms of the average stress. So again, just keeping in mind that our tau t here is constant. So if the thickness goes down, the stress level locally goes up. If the thickness goes up, the stress level goes down. And of course, for most situations, it's actually just going to be constant throughout. So your average stress there is just going to be the stress. And then just one thing to keep in mind, that this AM term here, that's the mean area within the boundary of the center line of the tube's thickness. Now again, if you have a relatively small difference if you have a relatively small thickness compared to the overall size of the structure, then that kind of the importance of that kind of goes away. Whereas if your walls are thicker, then kind of some errors that get introduced as a result of that become more and more important, which is why that this is the thin-walled tubes with non-circular cross-sections formula. So that's how we calculate the stress. If we want to calculate the twist, this can be done via some energy methods, which are beyond the scope of this course, to derive this equation. But you can do that to kind of figure out how much twist occurs over the length, over the length of a span of a thin-walled tube with a non-circular cross-section that has a torque applied to it. That having been said, I don't expect I will ever ask you a question for that, because this is an annoying integral, and it's not something that really is well suited for popping up in an exam, per se. Most of the time, I'll even say most of the time, these things are great for calculating your stresses. Some of to get a good idea of your stresses. Some of the times, for structures like this, kind of the localized loading conditions also come into play. So you may this is something that is often going to be a bit more suited for finite element analysis than perhaps you know it might be a bit more necessary than maybe uh, just a circular shaft or a tubular shaft would be. But yeah, that's how we go about doing those. So we'll do a couple examples of the kind of calculating the stresses for those, and of course we'll also do a couple examples of indeterminate problems involving angle of twist, both for ones where our T, L, and J are sorry, our T, J, and G are constant, and also at least one where we're varying.